Since this is an overview of all the foundational concepts, I want to devote a little bit of time to the 4 basic operations. In this video, I'm going to discuss how to perform addition and subtraction with large integers, decimals, and fractions. So first, large integers. Let's take, for instance, 248 and 135. So first, to add these together, what you want to do is you want to line things up at the decimal point. In this case, the numbers don't have anything past the decimal point, so you just line them up at the ends. You then start from the right and you add vertically. So we have 5 plus 8, that's equal to 13. And so we can't fit 13 in this single decimal place here, so we'll write a 3 and carry the 1. And so now when we go to add this column, we have 3 numbers in the column. And so we have to add 1, 4, and 3. And so together those are 8. And then we add 2 and 1 in the final column to get 3. So that's addition. Let's try out these same 2 numbers with subtraction. So we'll have 248, but this time minus 135. We'll subtract 5 from 8. 8 minus 5 is 3. Then we move to the next column. 4 minus 3 is 1, and 2 minus 1 is 1. And so that's subtraction with integers. Next, we'll go ahead and move on to decimals. Decimals are going to work largely the same way as integers, but with decimals, you have to be careful to line up the decimal point so that you're adding and subtracting in the right columns. So let's take 0.435 and we'll add 0.019. And so I've already done it here, but if you don't already have it lined up, what you want to do is line up the decimals, as I was mentioning back here. Line up the decimals vertically, so that way you know you have the right place values lined up. So we'll have 5 plus 9, which is 14. Again, we can't put 14 down here, so we have to carry the 1. Now we have 1 plus 3 plus 1, that's equal to 5. And then over here we just have 4 and 0, so we'll write a 4. And so now that we've added these, we need to make sure the decimal point drops in the right spot, and we'll add a leading 0. And so this is addition of decimals. We'll once again take the same 2 decimals and do subtraction. So 0.435 minus 0.019. Now we have 9 minus 5. Unfortunately, that's a negative number, so we have to borrow a 1 from over here. So this 3 is going to become a 2, and this 5 is going to become a 15. And so now we have 15 minus 9, and that gives us 6. 1 minus the 2, because we borrowed the 1 for the 15. 1 minus 2, or 2 minus 1, is 1. And then 4 minus 0 is just going to be 4. And once again, we'll drop the decimal and add the leading 0. And so this is integers and decimals, and those are both pretty straightforward. But then we have fractions. Fractions are easy enough if the denominator is the same. If the denominator is not the same, you have to convert one or both of the fractions to a different denominator before you can add or subtract them. So let's take, for instance, 1/3 and 1/6. We'll use these as our example this time. So 1/3 plus 1/6. We can't just add them together because the denominators are different. What we have to do is get a common denominator between the 2 fractions. To do that, you find the least common multiple of both of the denominators. In this case, the least common multiple is 6, because 6 and 3 both go into 6 evenly. 3 goes into 6 2 times, so we'll need to multiply 1/3 by 2 over 2, and that gives us 2 over 6. And so now what we have is 2 over 6 plus 1 over 6. Now that the denominators are the same, all we have to do is add the numerators together, and then we retain the same denominator as both of the fractions. So we have a 6 in the denominator, and 2 plus 1 is equal to 3. And so we have 3 over 6. So that's addition. We've already done the hard part of converting the two fractions, or of achieving a common denominator between the two fractions. So for subtraction, all we have to do is write the converted form. We have 2/6 minus 1/6, and just like we did above, we'll retain the 6 in the denominator, and then we'll just use subtraction on the numerators. So 2 minus 1 is 1. And so that is addition and subtraction for integers, decimals, and fractions. In this video, we're going to look at the last two of the basic operations, multiplication and division. So to start with, let's take the case of integers. Let's take 7441 and let's multiply it by 7. Alright, so we want to line up the two numbers at where the decimal point would be, right there, and then starting with the digit farthest to the right in the bottom number, in this case there's only one, but starting with that digit, we'll multiply by all the digits in the top number, starting with the one on the right. So we have 7 times 1, which is 7. 7 times 4, which is 28. So we'll put an 8 here and write a 2 up here. 7 times 4 is once again 28. But we have to add this 2, so we have 30. So this becomes a 0, and we add a 3 up here. Then we have 7 times 7, which is 49. Adding 3 more, we get 52. And so we can put the 5 in there. So that's multiplication for integers. If we had more digits in the bottom number, once we had finished multiplying the top number by this digit, we would then move on to this digit and multiply all those numbers, but start in this, this digit place, and then add up all the results at the end. But we just had one, so that's the answer. Division is a little bit more complicated. The way to do division, I'm going to be showing a method called long division. You write the number that you're dividing, and then to the left of that, you write the number you're dividing it by. And so in multiplication, we worked from right to left, but in division, we work from left to right. So we're going to take the digits individually if we can, and see how many times this number is going to fit into them. So first we have 7 going into 7. 7 can go into 7 one time, and 1 times 7 is equal to 7. So when we subtract this number from that number, we just get a 0. And so then we move on to the next digit. And I'll write a 4 here. 7 cannot go into 4 any times, so we'll write a 0 here, and we'll add the next digit. So 44 now. 7 can go into 44 6 times, so we'll write a 6 here. 6 times 7 is 42, and when we subtract that out, that leaves us with a remainder of 2. And so now we drag in the last digit, which is a 1. So we have 21, and 7 goes into 21 3 times. So 3 times 7 is exactly 21, and so we have a remainder of 0. So this is the full solution to this division problem. If 7 had not evenly gone into the last number here, we would have had to put a decimal point here and keep on going until it either terminated or we found a repeating pattern of digits, at which point we could stop. So this is multiplication and division for integers. I also want to demonstrate multiplication and division for fractions. It's much simpler particularly than the long division here. It's really just two different forms of multiplication. So let me demonstrate that. Let's say we have 1 over 3 times 3 over 4. Now, all we have to do to multiply fractions, we don't have to worry about common denominator or any of that like we do with addition and subtraction. We just multiply the two numerators. 1 times 3 gives us 3. And then we multiply the two denominators. 3 times 4 gives us 12. And so it's a lot easier in one sense to multiply two fractions than it is to add or subtract. And so that's really all there is to fraction multiplication. Fraction division just requires one extra step. And so what it's going to look like is if you have 1/3 divided by 3/4, that you take the reciprocal of the second number and then change the division sign to a multiplication sign. So this becomes 1 over 3 times, this was 3 over 4, so we'll take times 4 over 3. And so we flipped the fraction and changed it to a multiplication. And then all we have to do is just multiply numerator and denominator like before. 1 times 4 is 4, and 3 times 3 is 9. And so that is a brief review of multiplication and division for integers and fractions. In this video, I'm going to talk about exponents and roots. An exponent is a number that tells you how many times to multiply the base number by itself. So for instance, if we have 2 raised to the second power, like this, what this is telling us is that we need to multiply 2 times 2. Now, if we had 2 raised to the third power, this would be the same as 2 times 2 times 2. So the exponent is saying how many times to multiply this number by itself. A root is kind of the opposite of this. So let's take, for instance, 16. This is a radical symbol, and this tells us that we're taking a root. If there's no number up here, the number is assumed to be 2. So without any numbers up here, the radical sign designates a square root, or a root to the power of 2. So the square root of 16 is the number that has to be multiplied by itself twice in order to equal 16. So the square root of 16, by definition, if it is squared or raised to the second power, it equals 16. And so the square root of 16 is 4, because 4 raised to the second power, or 4 times 4, is equal to 16. And so roots and exponents are kind of inverse operations. But you can actually express roots as exponents. So for instance, if we wanted to go back to the square root of 16 here, we can write the square root of 16 as 16 to the 1/2. And so essentially, if you have 1 over a number in the as an exponent, you're essentially taking that number's root of the number in question. So like I was saying, the 2 up here that's omitted for a square root, that's the same as 1/2, a power of 1/2. You can also have other fractions or other powers of roots. So for instance, you might take 8 to the 1/3, or the third root of 8. So this would be a number that you have to multiply by itself 3 times in order to achieve this. So the third power of 8 raised to the third power is equal to 8. And so this number would be the same as 2, because 2 times 2 times 2, or 2 to the third power, is equal to 8. And a couple other things about exponents. Any number raised to the 1 is just the number itself. So 2 raised to the 1 is just 2. And any real number raised to the 0 is equal to 1. It doesn't matter if it's a positive number or a negative number. Any real non-zero number raised to the power of 0 is equal to 1. You may notice that all of the exponents and roots we've looked at so far here are whole numbers or fractions of whole numbers. You can, in fact, have roots that are, for instance, say this is 2 raised to the 2.3. You can have this sort of quantity, but it's not going to be easy to calculate by hand, and really you're going to want to use a calculator if you encounter anything that has a decimal in the exponent. So that's a good overview of exponents and roots. As I mentioned in the last video, a single linear equation can't be solved for specific values of x and y. It can only be solved for one variable in terms of the other variable. What that leaves us with, though, is a set of solutions, an infinite set of solutions that will satisfy the equation. So let me show you what I mean by that. Let's say we have the linear equation y equals 2x minus 1. Now we could plug any value of x into this equation and it would generate a value of y for which the equation would be correct. And so what you have is, as I mentioned, an infinite set of pairings that satisfy the equation. And we can represent that graphically with a line, because a line extends infinitely in both directions. And so by graphing a line, we can show graphically that any point on that line is a set of values for x and y that will satisfy a given equation. So this equation here can be graphed by substituting in for x a value of x and seeing what the resultant y value is and plotting that point, then plugging in a second value for x, getting a second y value and plotting that point. And because each line can be defined by 2 points, that will give us the line that represents this equation. So let's start out by plugging 0 in for x. By plugging 0 in for x, we get 0 minus 1, or negative 1, so y equals negative 1 when x equals 0. So we have our x-axis and our y-axis. When x equals 0 and y equals negative 1, that's this point right here. I'll go ahead and mark this 0, negative 1. So that's one point that's on this line, and it corresponds to x equals 0, y equals negative 1, which is one set of values that satisfies the equation. But let's plug in 1 now for x and see what we get. 2 times 1 is 2, minus 1 is 1. So when x equals 1, y equals 1. And if we plot that point as well, we get x equals 1, y equals 1, and another point that's on our line is right here. So now that we have 2 points, we can plot our line because 2 points can only represent, or can only lie on, one single line. And so this is the line that is the solution set for this linear equation. Now there are a couple of features that I want to point out about a graphed line that can tell us things about the equation that it represents. So in this equation, for instance, the line crosses the y-axis at negative 1. And this is what's called the y-intercept. The line intercepts the y-axis at a particular point, in this case negative 1. And the y-axis, or the y-intercept, when you have an equation of this form, is going to be this part of the equation right here. The part of the right side of the equation that doesn't have an x next to it. So that's the y-intercept. We also have what's called the slope. Now the slope of a line is defined as the change in the vertical coordinate divided by the change in the horizontal coordinate. And so for a given interval on this line, it doesn't matter how big the interval is, but we're just going to take the smallest one that we have graphed here. For any given interval, the slope is the change in the vertical divided by the change in the horizontal. In this case, the change in the vertical is 2. We go from -1 to 1. And the change in the horizontal is 1. We go from 0 to 1. So the slope here is 2 divided by 1, or just 2. And the slope, when you have an equation of this form here, is going to be the coefficient of the x term. And so this equation here is in what's called slope-intercept form. And I'm going to talk a little bit more about that in a later video. But these are just some of the key features to note on a graph of a line. You have the y-intercept and you have the slope, and you can either use the graph of the equation to find the equation, or you can use the equation to graphically show the solution set. I mentioned this briefly in my last video about the number line, but I want to go into a little more detail about integers, decimals, and fractions. The integers are the whole numbers that you see as tick marks on the number line. But in between each of these integers, you have these large spaces that you can't describe with just integers. You have to use other numbers to represent the space in between the integers. And to do that, we have decimals and we have fractions. Now, any number between two integers can be represented both as a fraction and as a decimal. To demonstrate this, I'm just going to enlarge essentially this section of the number line right here. So this section of the number line is now going to be represented right here. We have 0 over here and 1 over here. And we have this massive space in between where there are no integers. So to describe this, as I mentioned, we have decimals and we have fractions. I'll describe fractions first. Fraction is essentially a way to divide up this section inside of here into equally spaced segments. So if we put one right in the middle, we've cut it in half, or into 2 pieces. So 2 pieces, so we have a 2 on the bottom of our fraction. If we just go one of those 2 pieces, we have 1 over 2, or 1/2. And that is what this point here is. If we want to go further, we can divide it up into 4 segments. Now we have 4 equal segments. If we decide we want to go 1, 2, 3 of those segments, we can write this as a fraction with a 4 on the bottom because there's 4 parts, and we've gone 3 of them. So we write this as 3/4. And so you may notice that if you go 2/4, that's the same as going 1/2. So 1/2 and 2/4 are the same thing. And so this is kind of the idea of fractions. You divide up the space between the integers into equal parts, and you put that number on the bottom, or the denominator of the fraction. And then the number of those parts that you're counting is the number on the top of the fraction. And I've divided this up into 2 and then 4 because that's easy to draw. But you can divide up the space between the integers into as many sections as you like. You can divide it up into 3, you can divide it up into 5, 7, 10, any number of parts. And that's the number that'll go on the bottom. This provides a good transition into decimals. A decimal representation is essentially dividing up the space between 0 and 1 into 10 different segments. So I'll go ahead and see if I can draw that up a little bit. But so we've got 5 from here to here, 1, 2, 3, 4, 5, and then 6, 7, 8, 9, and 10. All right, so you've got the space between 0 and 1 divided up into 10 parts. With decimals, though, instead of saying, for instance, instead of writing this as 3/10, which is a valid way to write this particular point as a fraction, you would write this as 0.3. Because we use the decimal system, every number place to the right of the decimal means you've divided up this space between the two integers into 10 equal parts, and this is how many of the parts we're talking about. So we take the integer immediately beforehand and then count forward 3 of the 10 parts, and that gives us 0.3, which is the same as 3/10. And so you can take the space between any of these integers. For instance, if you wanted to take the space between 3 and 4 and count 6/10 of the way from 3 to 4, you would write this as 3.6, because you've gone 6/10 of the way from 3 to 4. And so you can describe any number on the number line using decimals or fractions. If you want to get even more specific than tenths, you can divide up, for instance, if you wanted to go somewhere between 0.3 and 0.4, you could divide this space up here into 10 equal parts, and then however many of those parts you went forward from 0.3, you would write that as another decimal here, so 0.3 and however many parts. So that is a quick overview of integers, decimals, and fractions. Now that we've laid a groundwork for multivariable equations by looking at linear equations, I want to look at systems of equations. Now, a system of equations is a set or a group of equations where the variables in however many equations you have represent the same quantities in each equation. So, for instance, if we have the system of equations 3x plus 4y equals 10, and 4x plus 8y equals 12, we have x and y in both of these equations, and this x are the same, and this y and this y are the same. And so you have essentially two pieces of information about these variables instead of one. And the general rule is that with systems of equations, if you have the same number of equations as you have variables, you can solve for values for the variables. You'll recall with a single two-variable equation, we couldn't solve for values for x and y. We could only solve for those variables in terms of the other variable. So with a system of equations, if we have the same number of equations as variables, generally we can solve for values for those variables. Now there are two exceptions to that rule. One is if the two equations are contradictory. So for instance, if you had the system of equations x plus y equals 5 and x plus y equals 1. These two equations are contradictory because they're telling you that the same quantity, x plus y, is equal to two different things. And this obviously can't be solved for values. The other situation where you can't solve for values is if the two equations are redundant. So for instance, if we have x plus y equals 2 and 2x plus 2y equals 4. These two equations are redundant because they tell us the exact same thing. If we divide each term in this second equation by 2, what we're left with is equation 1. And so it's really no better than having just one equation. We can't solve it for the values for these two variables. One way to think about solving systems of equations, at least linear equations like this, is to think about it graphically. The definition of what we're looking for here can be shown very easily on a graph. Let's say that this first line, the graph looks like this, and this second line, the graph looks like this. And we have some x and y axis here. Let's say this is x and this is y. This point right here is where these two lines intersect. And so this point has an x coordinate and a y coordinate. And the values of this x and y coordinate are the values for x and y that satisfy both of these equations. And so that's how you can kind of think about systems of equations graphically. And in this case here where we have the contradictory equations, this would essentially be parallel lines. The equations x plus y equals 5 and x plus y equals 1 would look something like this. You'd have these two parallel lines that never intersect. And so that's why you can't solve these for either variable. And in this case, with the redundant equations, this is as though you have one line drawn on top of another line. And so the solution for this is the entire line. So in both of these cases, there's no way to solve for x and y. But if you have the same number of equations as variables, and they're not contradictory and they're not redundant, you should be able to find what is graphically the intersection point and solve for values for the variables. In the next couple of videos, I'm going to demonstrate a couple of different methods for solving systems of equations.
Fractions. A fraction is a number that is expressed as one integer written above another integer with a dividing line between them, like x divided by y. So for example, 3/4. In this fraction, 3/4, the top number is called the numerator, and the bottom number is called the denominator. The numerator is the part that's being considered, while the denominator is the whole. So in this fraction, 3/4, we could take a pie shape and cut it into 4 pieces. That's our whole. And the part that's being considered is 3/4. So 1, 2, 3. So now you can see how much of our pie we're talking about, 3/4. We can manipulate fractions, and we do this by multiplying or dividing both the numerator and the denominator by the same number, not by adding and subtracting. We manipulate fractions to do many things. One thing is to compare them. If we were to compare 3/4 and 2/3, we would first need to find what's called a common denominator. Because in order to compare them, I need them to have the same denominator. So I can tell which one's bigger or if they're equal. So we'll take 3/4 and 2/3, and we're going to find a common denominator. When you do that, you want to look for multiples of the denominators. And the least common multiple will be the least common denominator. So the multiples of 4 and 3, 4 is 4, 8, 12, 16, etc. 3 is 3, 6, 9, 12, 15, 18, etc. So the least common multiple between 4 and 3 is 12. So that means I want to change this fraction to something over 12. Same with my other fraction. What I'm doing is creating an equivalent fraction. 3/4 is equal to something over 12. So I'm going to multiply my numerator and my denominator both by 3 to achieve that denominator of 12. So 3 times 3 is 9. And for so our fraction is 9/12. And then for 2/3, we'll do a similar thing. We want to change our denominator from 3 to 12. So we multiply 3 times 4 to get 12. And we must do the same to our numerator. 2 times 4 is 8. So now we can easily see which fraction is larger. 3/4 is equivalent to or equal to 9/12, and 2/3 is equal to 8/12. Well, 9 out of 12 is definitely more than 8 out of 12. So we could say that this fraction 3/4 is bigger than this fraction 2/3 if we were to compare them. So let's talk a little bit more about equivalent fractions. All of these fractions are equivalent fractions because they all represent the same value. 2/10, 3/15, 4/20, 5/25. And we could see that they represent the same value more easily by simplifying our fractions. So we said we can manipulate fractions by multiplying the numerator and denominator by the same value, or we can manipulate them by dividing the numerator and denominator by the same value. So if we wanted to simplify this fraction 2/10, we would just divide the numerator and the denominator by the same value. Both 2 and 10 are divisible by 2. So we divide our numerator by 2 and our denominator by 2. 2 divided by 2 is 1. 10 divided by 2 is 5. We do the same thing to our next fraction. 3 and 15 are both divisible by 3. So we divide our numerator by 3 and our denominator by 3. 3 divided by 3 is 1. 15 divided by 3 is 5. 4/20. Our numerator and denominator are both divisible by 4. So divide by 4, divide by 4. 4 divided by 4 is 1. And 20 divided by 4 is 5. Finally, 5/25. Numerator and denominator are both divisible by 5. 5 divided by 5 is 1. And 25 divided by 5 is 5. So as you can see, all 4 of these fractions are equal to 1/5. 1/5 is the simplest form of these fractions, and they are all equivalent fractions since they all have the same value, 1/5. Absolute value. Absolute value is the distance of a number from 0 and is always positive. It's denoted by a pair of vertical lines surrounding the value, such as the absolute value of 3. You can think of absolute value like you're being asked a question. And the question is, how far is 3 from 0? 3 is 1, 2, 3 places from 0. So the absolute value of 3 is 3. The absolute value of a negative number and its positive counterpart are the same. So the absolute value of negative 3 is also 3 because negative 3 is also 3 places from 0. 1, 2, 3 places from 0. The absolute value of a difference, when you're doing that, the order doesn't matter. Let's look at the absolute value of a couple of differences. The absolute value of 8 minus 3 and the absolute value of 3 minus 8. When you're doing the absolute value of a difference, again, the order doesn't matter. The result will still be the same. Let's see how that happens. Start on the inside finding your difference. 8 minus 3 is 5. So we have the absolute value of 5. And again, absolute value is the distance from 0. 5 is 5 places from 0. Now we'll look at the difference switched around. 3 minus 8. 3 minus 8, you could do add the inverse, so 3 plus a negative 8. 3 plus a negative 8 is negative 5, so we have the absolute value of negative 5. And like we talked about over here, the absolute value of a number and its negative counterpart are the same. So the absolute value of 5 and negative 5 is the same because, again, absolute value is the distance from 0, and distance can never be negative. So the absolute value of negative 5 is also 5, since negative 5 is 5 places from 0. Adding and subtracting decimals. When adding and subtracting decimals, first, line up the decimals. We have 4 and 23 hundredths plus 9 and 75 thousandths. Same with subtraction. 5 and 629 thousandths minus 45 hundredths. Then if you have any empty spaces, you can fill in with zeros. Adding zeros to the back of your number, to the back of a decimal, doesn't change the value of your number. So these numbers are still what they were. They're still equal. And then we just add or subtract like we usually would. 0 plus 5 is 5. 3 plus 7 is 10. So write your 0, carry your 1. 1 plus 2 is 3, plus 0 is 3. Bring that decimal down. 4 plus 9 is 13. So our answer, or our sum, is 13 and 305 thousandths. Now for subtraction. We're going to do the same thing, except now we're subtracting. 9 minus 0 is 9. 2 minus 5. We can't take 5 from 2, so we need to borrow from our 6, just like we usually would, and add a 1 onto our 2, which makes 12. 12 minus 5 is 7. And then 5 minus 4 is 1. We bring our decimal down. And 5 minus 0 is 5. So our result, or our difference, is 5 and 179 thousandths. Adding and subtracting fractions. To add and subtract fractions, first make sure that the denominators are the same. If they aren't, like in 5/9 minus 1/6, then we need to find the least common denominator. The least common multiple of 9 and 6 can be found by listing the multiples 9, 18, 27, etc. 6, 12, 18. Our least common multiple is 18. So we're going to change both of our fractions, 5/9 to something over 18, and 1/6 to something over 18. 9 times 2 is 18. So since we multiplied our denominator times 2, we must also multiply our numerator times 2. 5 times 2 is 10. 6 times 3 is 18. So we must also multiply our numerator times 3, and we get 3/18. So that means that 5/9 minus 1/6 is equal to 10/18 minus 3/18. Now we just subtract our numerators and put that difference over our denominator of 18. 10 minus 3 is 7. Then, if you can simplify the result, you should. But in this case, 7/18 cannot be simplified, so that's our answer. Let's look at an addition problem. Again, we've got to see if our denominators are the same, and if they aren't, then we need to change them so that they are. So we're going to find the least common denominator for 3 and 5, which means we're finding the least common multiple for 3 and 5. So I'll list the multiples: 3, 6, 9, 12, 15. And my multiples for 5, 10, 15. So my least common multiple is 15, which means I'm going to change both my denominators to something over 15. 2/3 equals something over 15. And 4/5 equals something over 15. So to get from 3 to 15, we have to multiply times 5. So we need to do the same to our numerator. 2 times 5 is 10. 5 to 15, we have to multiply 5 times 3. So we do the same to our numerator. 4 times 3 is 12, which means that 2/3 plus 4/5 is the same as 10/15 plus 12/15. And again, we add the numerators and put that result over our denominator. 10 plus 12 is 22. And this is an improper fraction since our numerator is larger than our denominator, so we'd want to change it to a mixed number. To change this improper fraction to a mixed number, we're going to divide our numerator by our denominator. 22 divided by 15 is 1, since 15 goes into 22 one time, with 7 left over out of, and the denominator stays the same. So 1 and 7/15 is our result.
Up here on the board, we have a sequence of numbers of 43, 31, 19, and 7. But notice after this comma, we have dot, dot, and dot, meaning there's more numbers after it. And so if we were going to continue this string of numbers, then we are going to have to figure out what the pattern here is with these numbers. So what we're going to do here is we're going to take this second term right here, and we're going to do the second term minus the first term. So the second term is 31 minus the first term, which is 43, which gives us negative 12. Now, if we were to continue that and do the third term minus the second term, then we get 19 minus 31, which again gets us negative 12. So we're realizing here that each successive number is 12 less than the one before it. So by looking at this, we can come up with an equation to represent this. And so this is the equation we've come up with. And because right here we start with 43, which is the first term we have. So we have n right here. So this represents how many numbers you are into the sequence. So say we're the first number into the sequence, it'd be 1 minus 1 equals 0 times negative 12 is 0. So we get 43. If this was the second term into the sequence, we'd have a 2 right here. So 2 minus 1 is 1 times negative 12 is negative 12 plus 43 is 31. So you can see how this equation works. But I'm going to quickly simplify this for us to make it easier. And so the way this was simplified is we just multiplied negative 12 times n by negative 1, and then added some numbers together. And so we got that right there, the simplified equation. So we're going to take this simplified equation right here, and we can use this to determine what number is going to come later in this sequence. So say we want to know what the 8th number in the sequence is. All we have to do is plug in 8 for n right there. So we take negative 12, we multiply it by 8 in parentheses plus 55. And so negative 12 times 8 equals negative 96 plus 55. And so I'll save you the math on that, but that equals negative 41. So the 8th term in the sequence is going to be 81. And you can do that for whatever number you want to put in for n. If you wanted to find the 72nd number in the sequence, you could do that. You could plug it in. Or maybe you just want to find the 5th number in the sequence. You could plug that in. And so you can see how you can take this sequence. You have to discover the pattern. Then you come up with an equation, and it's going to work for whatever number you want to plug in to n.
Associative property. The associative property states that when adding or multiplying a series of numbers, it does not matter how the terms are ordered. Remember that simplifying within the parentheses is the first step using the order of operations. So you can remember the associative property, the rule for the associative property, because the numbers are grouped or associated with one another. Let's look at a couple of examples. A plus B plus C is equal to A plus B plus C. So again, we're going to do what's in the parentheses first. Let's try this with 2 plus 3 plus 4 equals 2 plus 3 plus 4. So again, we're going to follow our order of operations, or PEMDAS. We're going to start by adding 2 plus 3, 5 plus 4, is equal to 2 plus, and again, following order of operations, 3 plus 4, which is 7. 5 plus 4 is 9, and that does equal 2 plus 7, which is also 9. So you can see it doesn't matter which terms we add first. Since we're doing addition, it doesn't matter what we do first. Let's see what happens when we do the multiplication side. So again, I'm going to use 2 times 3 times 4 is equal to 2 times 3 times 4. According to PEMDAS, we have to start inside our parentheses. So that's 2 times 3 times 4 is 12 is equal to, again, starting in our parentheses, 2 times 3 is 6 times 4. 2 times 12 is 24, and that does equal 6 times 4, which is also 24. Like the commutative property, the associative property is only true for addition and multiplication. Let's look what happens when we try to use it on subtraction and division. So if we tried to use the associative property, it would look like A minus B minus C, but again, it's not going to be equal to A minus B minus C. So I'm going to use numbers like 8 minus 4 minus 2 does not equal 8 minus 4 minus 2. Again, using order of operations, 8 minus 4 is 4, minus 2 does not equal 8 minus 4 minus 2 is 2. 4 minus 2 is 2, and that does not equal 8 minus 2, which is 6. As you can see, the associative property does not work on subtraction. Let's use it on division now. So with division, it would look like A divided by B divided by C, again, will not equal A divided by B divided by C. I'm going to use the same numbers we used for subtraction. So 8 divided by 4 divided by 2 does not equal 8 divided by 4 divided by 2. Let's simplify. Order of operations, 8 divided by 4 must be done first. 2 divided by 2 does not equal, again, parentheses first, 8 divided by 4 divided by 2 is 2. 2 divided by 2 is 1, and that does not equal 8 divided by 2, which is 4. And that's the associative property. Changing a number from standard form to scientific notation. To change a number from standard form to scientific notation, you need to first rewrite the number so that it is between 1 and 10 by moving the decimal to the left or the right. Let's look at 32,581. To write this in scientific notation, the first thing we have to do is take our decimal and move it to the left or to the right so that this number is between 1 and 10. Where's my decimal? It's at the end of my number. So I'm going to have to move it to right between my 3 and my 2 so that my number is now 3 and 2,581 10,000ths. Now we're going to multiply this times 10 raised to, and this power is found by determining how many places we had to move our decimal. We had to move it 1, 2, 3, 4 places, which means we would need to multiply this number times 10 to the 4th power to achieve our original number. So 32,581 is 3 and 2,581 10,000ths times 10 to the 4th power in scientific notation. This same pattern applies when expressing very small numbers in scientific notation. Let's consider the value 65 thousandths. We're going to start again by moving our decimal so that our number is between 1 and 10. So I'm going to have to move it to between my 6 and my 5. So that gives us 6 and 5/10. But right now these numbers aren't equal. Not until we add our times 10 raised to the, now we have to figure out the power. We moved it 2 places to the right. So we'd have to multiply 6 and 5/10 times 10 to the negative 2 power to achieve our original number. 65 thousandths is equal to 6 and 5/10 times 10 to the negative 2.
The processes for converting decimal numbers to fractions and percentages are both fairly simple, so I'll demonstrate both on each of these examples here. First, we have 0.35. To convert 0.35 to a fraction, we'll write the 2 digits in here as the numerator, and we'll take a look at the rightmost digit. The rightmost digit is 2 decimal places to the right of the decimal, so we're going to write 2 zeros in the denominator. So we have 35 over 100. And this can be reduced by dividing both the top and the bottom by 5. 35 over 5 is 7. 100 over 5 is 20. So this is equal to 7 over 20. To convert a decimal to a percentage, all we have to do is move the decimal point 2 places to the right. So 0.35 is equal to 35%. In the second example, we have 0.215. Once again, we'll write 215 as our numerator. The rightmost digit is 3 places to the right of the decimal, so we will write 3 zeros in our denominator. 215 over 1,000. We can divide top and bottom by 5, so 215 over 5 is equal to 43. and 1,000 over 5 is equal to 200. So this fraction is the same as 43 over 200. To convert to a percentage, we can just move the decimal point 2 places to the right. So 0.215 is equal to 21.5%. In this final example, we have 0.842. We will once again write these digits as our numerator. The rightmost digit is 3 places to the right of the decimal, so we will once again have 3 zeros in our denominator. 842 over 1,000. We can reduce by dividing top and bottom by 2. 842 over 2 is 421, and 1,000 over 2 is 500. So this fraction reduces to 421 over 500. To convert to a percentage, once again, we'll just move the decimal point 2 places to the right. So 0.842 is equal to 84.2%. The first step in converting a decimal to an improper fraction is to convert the decimal to a mixed number. So we'll convert to mixed numbers first. In this first example, we have 7.6. To convert this to a mixed number, we'll take the whole part, or the part to the left of the decimal, which is a 7, and then we'll take the part to the right of the decimal, which is a 6. Now, we can put the 6 over a power of 10, and there's only one digit to the right of the decimal, so there's only 1 0. So we have 7 and 6 over 10. Now we can reduce this fraction by dividing top and bottom by 2. So we have 3 on top and a 5 on the bottom. So this is equivalent to 7 and 3/5. Now to convert this to an improper fraction, we'll multiply the denominator by the whole number and then add the numerator. 5 times 7 is 35, plus 3 is 38. So we have 38 over 5. In this next example, we're going to once again take the whole number part, which is the 5, and then we will put the part to the right of the decimal over a power of 10. 2 places to the right of the decimal, so 2 zeros, 35 over 100. We can reduce this by dividing top and bottom by 5. 35 over 5 is 7. 100 over 5 is 20. So this is equivalent to 5 and 7 over 20. To convert to an improper fraction now, we'll multiply 20 times 5, which is 100, plus 7, which is 107. So we have 107 over 20. In the final example, we'll once again take the whole number part, 3, and then take the part to the right of the decimal, 375 over 3 decimal places, so 3 zeros, 375 over 1,000. Now, we can divide top and bottom here by 125, which leaves us with 3 over 8. So this number is equivalent to 3 and 3/8. Now to convert to an improper fraction, we'll once again multiply 8 times 3, which is 24, plus 3, which is 27. So we have 27 over 8.
Converting improper fractions to mixed numbers. To convert an improper fraction to a mixed number, first we're going to divide our numerator by our denominator. 22 divided by 5 is 4, with a remainder of 2. 4 is our whole number, while 2 is the numerator of our fraction, and the denominator stays the same. So 22/5 as a mixed number is 4 and 2/5. Let's look at one more. Again, to change an improper fraction to a mixed number, we're going to start by dividing our numerator by our denominator. 18 divided by 4 is 4. 4 times 4 is 16, so we have a remainder of 2. 4 goes into 18 4 times with a remainder of 2 out of 4, since our denominator stays the same. This mixed number is special because we can simplify this fraction 2/4. And when you can simplify, you always want to do that. So 4 and 2/4 simplified would be 4 and 1/2. Since the GCF of 2 and 4 is 2, we divide both numerator and denominator by 2. 2 by 2 is 1, and 4 divided by 2 is 2. So 18/4 as a mixed number is 4 and 1/2.
The processes for converting improper fractions to mixed numbers and decimals share the same first step. I'll demonstrate with a few examples. In this first example, we have 34/5. The first step is to see how many times the denominator will go into the numerator and see what the remainder is. So 5 will go into 34 6 times with a remainder of 4. So this mixed number equivalent is going to be 6 and 4/5. Now, we've already got our first step completed. We have the whole number, so we take the whole number and put it to the left of the decimal, and then we take the fraction down here, and we need to convert the fraction to another fraction with the denominator that's a power of 10, so 10 or 100 or 1,000. In this case, we can convert it to a denominator of 10 by multiplying top and bottom by 2, so this is equivalent to 8/10. Now we can take the numerator and put it to the right of the decimal, so our decimal equivalent is 6.8. In the second example, we have 29/4. 4 goes into 29 7 times with a remainder of 1, so our mixed number equivalent is 7 and 1/4. Now we take the whole number, put it to the left of the decimal, take the fraction, and now we have to convert the fraction to a power of 10 in the denominator. 4 won't go into 10 evenly, but it will go into 100. So we'll multiply top and bottom by 25, and that gives us 25/100. So now we can take the numerator and put it to the right of the decimal, 7.25. In this final example, we have 63/8. 8 goes into 63 7 times with a remainder of 7. So we have 7 and 7/8. Once again, we'll pull down the 7, put it to the left of the decimal, and then convert this fraction to a denominator of a power of 10. Since the denominator is 8, we're going to have to go with a denominator of 1,000. So to do that, we'll multiply top and bottom by 125. This gives us a denominator of 1,000 and a numerator of 875. Now we can take the numerator, put it to the right of the decimal, which gives us a decimal equivalent of 7.875.
Decimals. Decimals use place value to represent an amount. To read a decimal, like we have here, first read the number to the left as a whole number, followed by and, then read the number to the right of the decimal, followed by the last place value. So this number would be read as 641 and 5,129 10,000ths. This number could also be represented as a mixed number. 641 and 5,129 10,000ths. Let's look at another decimal. 5 and 8,139 10,000ths. We could write this number as an improper fraction by taking the 5 plus, this would be 8/10, since it's in the tenths place, plus 1/100ths, plus 3/1000ths, plus 9/10,000ths, which would give us 58,139 10,000ths. So we've seen a decimal in decimal form. We've seen it represented as a mixed number and also as an improper fraction. Distributive property. The distributive property involves multiplying over grouped addition or subtraction terms. It states that you multiply the number outside of the parentheses by each term inside of the parentheses, and then add or subtract as in the original. You can think of distributing as handing out or giving something out. You're giving out the number on the outside of the parentheses to the numbers on the inside of the parentheses. We're going to look at two examples, one with addition and one with subtraction. If we were doing 2 times the quantity 5 plus 3, then we could use the distributive property to simplify this by distributing the 2 to the 5, 2 times 5, plus 2 times 3. Then we would simplify. According to PEMDAS, we need to multiply first. So 2 times 5 is 10, plus 2 times 3 is 6. Finally, we combine 10 plus 6 for 16. Let's look at this subtraction problem. If we wanted to simplify 4 times the quantity 5 minus 2, we would start by multiplying 4 times 5 minus 4 times 2. And then we would simplify. Following the order of operations, we're going to multiply first. 4 times 5 is 20 minus 4 times 2 is 8. And 20 minus 8 is 12. Dividing decimals. To divide decimals, first move the decimal point in the divisor so that it's a whole number. Then move the decimal point in the dividend the same number of places. And finally, move the decimal point up so that you know where it goes in your answer. So this means that now we're dividing 25 into 789 and 5/10. Now we just divide as we would with whole numbers until we get no remainder, or you know it's a repeating decimal. So 25 goes into 78 3 times. 25 times 3 is 75. We subtract and we get 3. Bring down the 9. And 25 goes into 39 1 time. 25 times 1 is 25. We subtract. 9 minus 5 is 4. 3 minus 2 is 1. Then we bring down our 5. 25 goes into 145 5 times. 25 times 5 is 125. Then we subtract. 5 minus 5 is 0. 4 minus 2 is 2. And then we have to add on a 0 so that we can continue. Since our remainder isn't 0, we still have 20 here. We need to add on a 0 to bring down, because we can add as many zeros after our decimal place as we like without changing the number. 25 goes into 200 8 times. 25 times 8 is 200, so that when we subtract, we get a remainder of 0. Now that we've reached a remainder of 0, we're finished dividing, and our result is 31 58/100.
When dealing with fractions of a whole, realize that there's a numerator and a denominator in every fraction. So the numerator is on top and the denominator is on the bottom. So we have a fraction bar right here. And so first, we need to determine what goes in the denominator. So that's the total of amount of spaces we have on the fraction strip. So we have the fraction strip right here, so we need to count the total amount of spaces. So count with me. 1, 2, 3, 4, 5, 6, 7, 8. So we need to put an 8 in the denominator here. Now when it comes to the numerator, we need to count the shaded spaces. And so notice these spaces right here, they're all shaded. So now we need to count those. 1, 2, 3, 4, 5. So there's 5 shaded spaces. And so the 5 is going to go in the numerator because we have the whole amount right here and then we have part of the whole. So right here we have a pizza. And so let's count the spaces of this pizza. 1, 2, 3, 4, 5, 6, 7, 8. So again, if we're doing a numerator and a denominator, we put 8 in the denominator. So now we need to count the shaded regions for the numerator. So there's 1, 2, 3, 4, 5 shaded regions. So here for this pizza, there were 8 total pizzas, so 8 is the whole. And then 5 is how many are still there. So there's 5 pieces of pizza still there. So 5 goes in the numerator. So although you may mostly be dealing with a fraction strip, try to take that idea right there and think about just a pizza and think about, okay, maybe there's 8 or 5 total pieces of pizza and how many have not been eaten yet. And so that's what you're doing when you look at a fraction strip. So remember that the whole goes in the denominator and then the shaded regions go in the numerator.
Graphs of functions. The first graph is a linear function. It graphs a line. The second graph is what's called a quadratic function. Quadratic functions graph a U or a parabola. The third graph is an exponential function. Exponential functions start out increasing very slowly and then start increasing more and more rapidly. This next graph is the graph of a logarithmic function. A logarithmic function is the inverse of an exponential function. We should also talk about the asymptotes of an exponential and a logarithmic function. An exponential function has a horizontal asymptote of y equals 0. While a logarithmic function, since it's the inverse of an exponential function, has a vertical asymptote of x equals 0. And an asymptote is just a line that the graph is approaching but doesn't cross. The next graph is what's called an absolute value function. And it graphs a V. It looks like a V. So they're straight lines, and then the left side is just the reflection of the right side. This next graph is the graph of a square root function. And a square root function is a parabola turned on its side, and it's just the top half of the parabola turned on its side. And then the last function is the graph, this is the graph of a rational function. And rational functions have two branches, one in the first quadrant and one in the third quadrant. If you look at this branch here, as we move from left to right, it's decreasing. And the same with the other branch, as we move from left to right, it decreases. And so there are some of the basic functions and their graphs. Greatest common factor. The greatest common factor, or GCF, of two numbers is the largest value that divides into each of the numbers. Let's take, for instance, 18 and 30. You can find the GCF of two numbers by finding the prime factorization of your numbers and then finding what they have in common. So the prime factorization of 18 is even, so it's divisible by 2. So 2 times 9 would be 18. 9 is not prime though, so we need to break 9 down. And the factors of 9 are 3 times 3. So the prime factorization of 18 would be 2 times 3 times 3. 3 times 3 is 9, times 2 is 18. I always like to check after I've factored to make sure I've got it. The prime factorization of 30. 30 is divisible by 2 also, since it's even. So 2 times 15 would be 30, but 15 is not prime. So we have to break it down into its prime factors. And 15's prime factors are 3 times 5. So the prime factorization of 30 is 2 times 3 times 5. 2 times 3 is 6, and 6 times 5 is 30. Now again, to find the GCF, we're going to look for what they have in common. 18 and 30 have 2 and 3 in common as prime factors. So we take those factors they have in common and multiply them. 2 times 3 is 6, so the GCF of 18 and 30 is 6. 6 is the largest factor that these numbers have in common. Least common multiple. The least common multiple, or LCM, of two numbers is the smallest value divisible by both the numbers, or it's the smallest number that both of your numbers divide into evenly. The LCM can be found by finding the GCF, or greatest common factors, and the remaining factors. The LCM is the product of the GCF and those remaining factors. For example, if we wanted to find the LCM of 18 and 30, we would first need to factor them. 18 is 2 times 9. Since 9 is not prime, we would factor 9 to 3 times 3. 30 is also even, so we'll start with 2. 30 is 2 times 15. 15 is not prime, so we factor 15. 15 is 3 times 5. The GCF, or greatest common factor, is 2 times 3, or 6. So our least common multiple is the product of our GCF, 6, and the remaining factors. The remaining factors are 3 and 5. So 6 times 3 times 5. 6 times 5 is 30. 30 times 3 is 90. So the smallest number that 18 and 30 will both divide into evenly is 90. Linear equations. Marielle has 10 coins in her pocket. All of them are quarters and dimes, and their total value is $1.60. How many of each type of coin does she have? We can solve this by using a system of equations. We're told that she has 10 coins in her pocket and that they're all quarters and dimes. So if we use D for the number of dimes and Q for the number of quarters, then one of our equations could be her number of dimes plus her number of quarters is 10 total coins. Next, we're told that the total value is $1.60. Well, dimes are worth 10 cents. So 10 times however many dimes she has, plus quarters are worth 25 cents, so 25 times however many quarters she has will give us a total of 160. We've eliminated the decimal, so we just move the decimal over 2 times to the right for all of our numbers. So instead of 10 cents, we have 10. Instead of 25 cents, we have 25. And instead of $1.60, we have 160. But you could leave the decimals in there if you wanted to. Now to solve this system, we've got 3 options. We could graph both of these and see where they intersect. We could use substitution or elimination. And it's your choice. For this particular problem, I'm going to use substitution. So I'm going to solve for D in my first equation so I can substitute it in my second equation. So D is equal to, and I have to subtract Q from both sides, so negative Q plus 10. To solve for D, subtract Q from both sides, and you get negative Q plus 10. So in my second equation, I'm going to use negative Q plus 10 to substitute for D. So we have 10 times the quantity instead of D, negative Q plus 10, plus 25Q is equal to 160. Now we can solve for Q. To do that, first we need to distribute. 10 times negative Q is negative 10Q. 10 times 10 is 100, so plus 100, plus 25Q equals 160. Now to solve for Q, we need to combine like terms. Negative 10Q plus 25Q is 15Q. Plus 100 is equal to 160. Subtract 100 from both sides, and we get that 15Q is equal to 60. Now we divide both sides by 15. 15 divided by 15 is 1, and 1 times Q is just Q. We get that Q is 4, which means she has 4 quarters. So how many dimes does she have? Well, we know that her number of dimes is equal to negative Q, so negative 4, plus 10. So her number of dimes is negative 4 plus 10, 6. So we can say Marielle has 4 quarters and 6 dimes in her pocket. Multiplying decimals. When multiplying decimals, instead of lining up the decimal point, we line up the last digits on the right. So if we were multiplying 4 and 23 hundredths times 9 and 75 thousandths, we'd want to line up our last digits. So 3 is the last digit in 4 and 23 hundredths, and 5 is the last digit in 9 and 75 thousandths. There's my 7, my 0, my decimal, and 9. Now we multiply just like we multiply whole numbers. So starting with 5, 5 times 3 is 15, carry the 1. 5 times 2 is 10, plus 1 is 11, carry the 1. 5 times 4 is 20, plus 1 is 21. And then I'll get rid of these. For our next number, now that we're multiplying times the 7, we need a 0 placeholder. 7 times 3 is 21. Write your 1, carry your 2. 7 times 2 is 14, plus 2 is 16. Write your 6, carry your 1. 7 times 4 is 28, plus 1 is 29. Get rid of those. Then we need 2 zeros for placeholders. And when we multiply times 0, 0 times 3 is 0, 0 times 2 is 0, and 0 times 4 is 0. We just get a line of zeros. So moving on to our last digit, now we need 3 0 placeholders before we multiply times 9. 9 times 3 is 27. Write the 7, carry the 2. 9 times 2 is 18, plus 2 is 20. Write the 0, carry the 2. 9 times 4 is 36, plus 2 is 38. Then just like we would with any other whole numbers, we're going to add our results together. 5 plus all these zeros gives us 5. 1 plus 1 is 2. 1 plus 6 is 7. 2 plus 9 is 11. Plus 7 is 18. Write our 8. Carry our 1. 1 plus 2 is 3. And then we have 8 and our 3. To determine where the decimal point goes when you've multiplied your decimals together, we're going to take how many numbers there were behind our decimal in our first number and how many numbers there were behind our decimal in our second number and add those together. So since we had 2 numbers behind the decimal here and 3 numbers behind the decimal here, then our result will have 5 numbers behind the decimal. 2 plus 3 is 5. 1, 2, 3, 4, 5. So this is the result of multiplying my 2 decimals together. Ordering decimals. When ordering decimals, place value is very important. We're going to begin by looking at the numbers to the left of the decimal. So if we look at our numbers, to the left of the decimal, if we're ordering these numbers from least to greatest, then the smallest number to the left of our decimal is this whole number, -3. -3 is the smallest whole number out of our whole set. So -3 and 68 hundredths would be our first decimal, least to greatest. So we're going to look for our next biggest, which means we're still looking at our whole numbers. So again, looking at our whole numbers, the next whole number, the next biggest, would be 56 thousandths, because the whole number 0 is greater than -3, but it's smaller than these whole numbers 2 and 3. So our next number would be 56 thousandths. So again, we're going to look for the next greatest whole number. So looking at our whole numbers again, 3, 3, 2, and 2, 2 is going to be our next number. 2 is smaller than 3. But we have two of them. We have two numbers with the whole number 2 in front. So we've got to move to our next place, our tenths place, and look at the tenths place to see which of our numbers would be the next in our line from least to greatest. So looking at the tenths place, this number, 2 and 2,344 ten-thousandths, has a smaller number in the tenths place than our other decimal does. So since we're ordering from least to greatest, this number would be next. Followed by 2 and 3,872 ten-thousandths, since it was the next because of our whole numbers. So we're done with our 2's, moving on to our next whole number. These two are the last ones I have, and again, they have that same whole number. So then we'd move to the tenths place to compare our tenths place and see which one is smaller. Looking at our tenths place, again, they have the same number. So still we don't know which one's going to come next. So we move on then and look at the hundredths place. Looking at the hundredths place, they're still the same. So right now we still can't tell which one's bigger, which one's smaller. So we move one more place over to the thousandths place. Looking at the thousandths place for this number, we have a 2 in the thousandths place. But looking at 3 and 57 hundredths, there is no number in the thousandths place. When you're missing a number after your decimal, it's always 0. In fact, you could fill in as many zeros after each one of these numbers as you wanted to. It doesn't change your number. So since this number has a 0 in the thousandths place, and this decimal has a 2 in the thousandths place, that means this number is smaller, so it'd be our next number in the series. So 3 and 57 hundredths, followed finally by 3 and 572 thousandths. So when you're ordering decimals, start by looking at your whole number and ordering that from least to greatest. If your whole numbers are the same, like they were here, then look at the tenths place and see which one is smaller in your tenths place. If, like in these numbers, you have the same whole number, the same number in the tenths place, then you move to the hundredths. If those are the same, you move to the thousandths, and so on until you find the numbers from least to greatest. Ordering fractions. When ordering fractions, you must first look at the denominator. If the denominators of the fractions are the same, then you order them according to the numerators, with the values increasing left to right. Let's look at an example. You can see all the denominators are the same. So we're going to order these fractions by looking at our numerators. If we're ordering them from left to right, or from least to greatest, then the smallest number would be our biggest negative number, -7/9. Our next number would be our next negative number, -4/9. Next biggest would be our first positive number, 2/9. And finally, 4/9. Now let's look at some fractions that don't have the same denominator. For these fractions, we could first find the least common denominator, so that we could have all the same denominator and then order them by the numerator. The least common denominator, or LCD, for 4, 12, 2, and 6 would be 12. So first, we're going to convert all these fractions to have the denominator of 12. 3/4. To convert 3/4 to something over 12, we'd need to multiply 4 times 3. So we'll do the same to our numerator. 3 times 3 is 9, and 4 times 3 is 12. So 3/4 is 9/12. Negative 7/12 already has our least common denominator of 12, so we're going to leave it alone. 1/2, 2 would need to be multiplied by 6 to get 12, so we'll do the same to our numerator. 1 times 6 is 6, 2 times 6 is 12. Negative 5/6. 6 would need to be multiplied by 2 to get 12, so we'll do the same to our numerator. 5 times 2 is 10, 6 times 2 is 12, and of course, it's still negative. Now we can order our fractions based on their numerators, from least to greatest, from left to right. Our smallest number is our biggest negative, which is negative 10/12. Then our next negative, negative 7/12. Then 6/12. And finally, 9/12 would be our largest number. Order of operations. Before simplifying expressions, it is important to know which operations to perform first if more than one operation is present in the expression. Please excuse my dear Aunt Sally, or PEMDAS, is often used for remembering the order of operations. P is for parentheses. Anything in parentheses should be done first. This one's a little misleading though, because it's not just parentheses that should be done first, it's all grouping symbols. Brackets, absolute value, anything that groups numbers together. Followed by exponents, and then their inverses, roots, should be done next. Following that is multiplication and division. And this is special because multiplication and division, it's not that one needs to be done before the other. These are just worked from left to right. So in your expression, when you're looking from left to right, you'll do all your multiplication before you do your division. Finally, addition and subtraction work the same way as multiplication and division. So these will also be done from left to right, but these will be the last things done when simplifying an expression. Let's put PEMDAS to work. We're going to simplify this expression. So according to PEMDAS, we need to start with our parentheses, or our grouping symbols. 3 plus 9 then is where we need to start. That's the only thing we're going to simplify, so everything else stays the same. 2 plus 5 minus 3 plus 9 is 12. Divided by 2 squared. We're done with our parentheses or grouping symbols, so next up is exponents. And we have an exponent right here at the end, so 2 squared will be the next thing we simplify. 2 plus 5 minus 12 divided by 2 squared means 2 times itself 2 times, which is 4. Then we have our multiplication and division from left to right. So as I look from left to right, all I have is this one division operation to perform. So that'll be the next thing we do. 2 plus 5 minus 12 divided by 4 is 3. Finally, we get to our addition and subtraction. Again, these are worked from left to right. So 2 plus 5 is 7. Bring down our minus 3, and 7 minus 3 is 4. So this expression, simplified, would give you 4. Now let's see what happens if we ignore the order of operations and just work from left to right. If we were just working from left to right, we would start with 2 plus 5, which would give us 7, minus 3 plus 9, divided by 2 squared. Then we would do our 3 plus 9, so we'd have 7 minus 12 divided by 2 squared. 7 minus 12 would give us negative 5, since we can add the inverse. 7 plus negative 12, negative 5, divided by 2 squared. Negative 5 divided by 4 is negative 5/4. So as you can see, if we ignore the order of operations, we get a completely different answer, which is why it's very important to make sure you're always going in the correct order whenever you solve or simplify an expression.
Prime factorization of a number is a number written as a multiple of prime numbers. Again, a prime number is a number that's only divisible by 1 and itself, meaning it only has factors of 1 and itself. Let's look at some examples of prime factorization. Now, what two numbers we can come up with that equals 30 when we multiply them? 6 and 5. Now, 5 is a prime number because it's only divisible by 1 and itself 5. But 6 is a composite number, which means there are other numbers other than 6 and 1. When you multiply them, they will equal 6. You also have 3 and 2. 3 is a prime number and 2 is a prime number. So when you multiply 3 times 2 times 5, you come up with 30. 3 times 2 is 6 times 5 equals 30. Let's prime factorization 40 as well. Again, two numbers, when you multiply them, they equal 40. 4 and 10. 10 times 4 equals 40. 4 and 10 are composite numbers. They're not prime numbers. 4 and 10 are composite numbers. Why are they composite numbers? Because they're not only divisible by 1 and itself, they're also divisible by other numbers. So we look at 4. 4 is obviously divisible by 1. It's divisible by 4, but it's also divisible by 2, because 2 times 2 will equal 4. Then 10. 10 is a composite number because other than 1 and itself, 10, it has two other numbers. 5 and 2, when multiplied, equals 10. So 10, 5, and 2. Now, 2 is a prime number. It's only divisible by 1 and itself, 2. As we said over there with number 30, 5 is a prime number. Now, when we multiply these prime numbers, 2 times 2 times 5 times 2, we come up with 40. So 2 times 2 is 4 times 5 times 2. Then 4 times 5 is 20 times 2. And then 20 times 2 is equal to 40. This is how we do prime factorization.
Prime number. A prime number is a natural number higher than 1 that cannot be divided by any other natural number besides 1 and itself. Here is a list of the first 7 prime numbers. 2 can only be divided by itself and 1. 3 can only be divided evenly by itself and 1. 5, the same. 7, so on and so forth. Notice that in our list of prime numbers, the number 1 is missing. 1 is not considered a prime number since it doesn't have 2 divisors or 2 factors. 1 can only be divided by itself, 1. So to be a prime number, you have to be able to divide it by 2 numbers, 2 and only 2. Like on 2, we can divide it by 2 and by 1 but nothing else will divide 2 evenly. Notice also we're missing the number 4. 4 is not a prime number because it can be divided by 1, 2, and 4. So it can't only be divided by itself and 1. That's the same with 6, 8, 9, 10, etc. Those kinds of numbers are called composite numbers. So prime numbers are numbers that can only be divided by 1 and itself, and composite numbers would be all the other numbers. However, 1 is neither. 1 is neither prime nor composite. It's special. Rates and unit rates. Ratios are considered rates when they compare two different units, like miles per hour or cost per ounce. A unit rate is one in which the numerator of the fraction is compared to a denominator of 1 unit. That way you can tell, for instance, like how much just 1 ounce of something costs. And you'll see unit rates a lot at the grocery store. Under or next to the price of an item, it'll tell you how much that item costs for every 1 ounce or for every one thing in the package. So let's look at a problem dealing with rates and unit rates. Dave is driving 240 miles to his aunt and uncle's house. If he gets there in 4 hours, how many, and here's the key right here in the question, how many miles per hour did he drive on average? In that question, they're telling you how to set up the problem. They're telling you to put miles over hours. So we're going to start with that. Miles per hour. And now we can substitute the information in from the problem. So they told us how many miles. He's going 240 miles. And they told us how many hours. 4 hours. So we can put that into our rate, 240 miles for his 4 hours. So right now this would be considered a rate since we have two different units, our miles and our hours. But to determine our unit rate or to figure out his average, we would need to divide or simplify our rate to find our unit rate. So if we want to have a denominator of 1, then we're going to have to divide 4 by 4 to get our 1. And if we divide our denominator by 4, then we must also divide our numerator by 4. 240 divided by 4 is 60. So again, this is miles per hour. So what this unit rate tells us is that on average he was going 60 miles for every 1 hour. So your answer could be written as 60 miles per hour is how fast Dave was going on average. Scientific notation. Scientific notation is a way to express very large or very small numbers in the form a times 10 to the b, where a is a number between 1 and 10, and b is an integer. We're going to focus on this last part, 10 to the b, or 10 raised to an integer, first. So let's look at 10 to the first power. 10 to the first power is 10 times itself 1 time, or just 10. 10 squared is 10 times itself 2 times, or 100. 10 cubed is 10 times itself 3 times, or 1,000. And 10 to the fourth power is 10 times itself 4 times, or 10,000. Notice as our exponent increases, so does our place value of the result. as you increase your exponent, it's really like you're moving your decimal place one place to the right. Let's look and see what happens when we raise 10 to a negative exponent. To simplify a negative exponent, we're going to take the reciprocal, so we're going to flip it, of the number containing a positive exponent. So the reciprocal would be 1 divided by 10 to the first, or just 1/10. And 1/10 as a decimal is 1/10. We'll do the same for 10 to the negative 2. So we take the reciprocal with the positive exponent, 1 divided by 10 squared, which is 1 divided by 10 squared is 10 times 10, which is 100, or 1/100th as a decimal. 10 to the negative 3 is 1 divided by 10 to the third power, which is 1 divided by 1,000, or 1/1000th. And then finally 10 to the negative 4, 1 divided by 10 to the fourth, which is 1 divided by 10,000, or 1/10,000th. And so we looked at this because with scientific notation, we would take a number like 3 times 10 to the second power. And what 3 times 10 to the second power is really 3 times 10 squared, which is 100. 3 times 100 is 300. Or what you can do is, since it's times 10 to the second power, you can take the decimal on 3 and just move it 2 places to the right. Since we saw that's what happened with our tens raised to the different exponents, we just moved the decimal 1 place to the right as our exponent increased. So we can take our decimal on 3, which if you can't find one, it's at the end of the number, and move it 2 places to the right to get the answer 300. 3 times 10 to the second power would be 300. Let's look at a number raised to a negative exponent, like 4 times 10 to the negative third power. So here, when we had 10 to the negative first, 10 to the negative second, etc., notice that as our exponents were decreasing, also our values were decreasing by one decimal place each time. Our numbers got smaller and smaller and smaller. Our decimal was moved 1 place to the left each time. So we're going to do the same thing with 4 times 10 to the negative third. It would be 4 times, and 10 to the negative third we saw was this 1/1000th. So it's like 4 times 1/1000th, which is 4 times 1/1000th, which is 4/1000ths. And the other way to do this is just to take that to the negative 3, take that power, and this negative third power just means to move your decimal 3 places to the left. So we would take our 4, and our decimal is behind it, and just move it 1, 2, 3 places to the left, which is the same result we got by doing it the other way. Solutions of a quadratic equation on a graph. The first graph we have here is a parabola which crosses the x-axis 2 times, which means there are 2 solutions to this equation, y equals x squared plus x minus 6. And those 2 solutions are the places where the parabola crosses the x-axis. This one has 2 solutions, and those 2 solutions are positive 2 and negative 3. So x equals negative 3 and positive 2. Those are the 2 solutions. However, the parabola won't always cross the x-axis 2 times. Sometimes it may only intersect it 1 time. And when that happens, it's the vertex that touches the x-axis one time. And so this intersection, this parabola, this graph would only have one solution. And the solution here is the vertex where it intersects the x-axis at positive 3. So here our solution would just be x equals 3. The third situation is when the parabola never touches the x-axis. That would be when you had two complex solutions or no real solutions. And again, those would be two complex solutions because it never actually touches the x-axis, so there aren't any real solutions to the quadratic equation. So here are three different situations. You can have two solutions to your equation, one solution, or none at all. And you can tell what those solutions are just by looking at the graph of the parabola for the quadratic equation. You can see if it crosses twice, and those would be your two solutions. If it only intersects your x-axis one time, and that's your one solution. Or if it never touches the x-axis at all, and that means that the solutions are complex and they are not real.
One of the most basic concepts in algebra is the single variable equation. A single variable equation consists of a variable, usually x, and some other numbers, and all you have to do to solve it is isolate x on one side of the equation by performing the same operations to both sides of the equation. So let's look at some examples here. In this first one we have x plus 13 equals 25 minus 19. So to isolate x, we need to get this 13 to the other side of the equation. To do that, we need to subtract 13 from both sides of the equation. So this will cancel, and what we're left with is x equals 25 minus 19 minus 13. And so now all we have to do is solve this part over here, and we've got the value of x. So let's do these one at a time. X equals 25 minus 19 is 6. So x equals 6 minus 13. And 6 minus 13 equals negative 7. So in this equation, x equals negative 7. In the second example, we have 10 minus x plus 38 equals 54 minus 17. Now, in this equation, we have a negative x, so the first thing we want to do is get x to be positive. So to do that, we can add x to both sides of the equation, and that'll give us 10 plus 38 equals 54 minus 17 plus x. Okay, the next step is going to be to move these numbers over to this side so that x is over there by itself. So we need to subtract 54 from both sides and add 17. So what we have now is x equals 10 plus 38 minus 54 plus 17. And so once again, we'll just do these one at a time. 10 plus 38 is 48. 48 minus 54 is negative 6. And negative 6 plus 17 is 11. So in this equation, x equals 11. When you're faced with a complex single variable equation like this one, the first thing you want to do is remove the fractions from this by multiplying both sides of the equation by the product of the two denominators. So we're going to multiply the left and right sides of the equation by 3 times x. So if we multiply this side by 3 times x, what we get is we can cancel out this x, and what we're left with is 3 times 3x plus 17 minus 11. If we multiply the right side of the equation by 3x, we can cancel out the 3, and what we're left with is 10x. So now we just have to solve this for x. This 3 gets distributed to each of these terms, so 3 times 3x is 9x, plus 3 times 17 is 51, minus 3 times 11 is 33, equals 10x. Now, the next thing we want to do is get x all by itself on one side of the equation. So we're going to subtract 9x from both sides, and that'll cancel this out, and that'll leave us with just x over here. And we still have the 51 minus 33. Now to solve for x, all we have to do is subtract 33 from 51, and the solution to that is going to be 18. So that is how you solve an equation like that. To solve a single variable equation, all you have to do is isolate x on one side of the equation and move everything else to the other side. And you do that by performing the same operations on each side of the equals sign. In this example here, we're going to have to use multiplication and division to isolate x. So the first thing we want to do in solving this problem is to rewrite it in a simplified form. Because what we have is 3x times 12 divided by 5 equals 2x times 15x divided by 20. So let's simplify this a little bit. We have 3x times 12, which is 36x, divided by 5, and that's equal to 2x times 15x, which is 30x, divided by 20. 30x squared. So the first thing we want to do is get x all by itself on one side. So we'll divide both sides of the equal sign by x, and that gives us 36 over 5 equals 30x over 20. Now the next thing to notice is that you can reduce this fraction from 30 over 20 to 3 over 2. So we have 36 over 5 equals 3 over 2x. And now what we want to do is get this all by itself over here. So we need to move the 3 over 2 onto this side of the equation. And to do that, we're going to multiply both sides by 2 over 3. So 3 over 2x times 2 over 3. The 2's are going to cancel and the 3's are going to cancel, leaving us with x. On this side, when we multiply by 2 over 3, we see that we can cancel the 3 here. So 3 over 3 is 1. 36 over 3 is 12. So what this leaves us with is 24 over 5. So x equals 24 over 5 is our solution. If we want to write this as a mixed number, we can say that x equals 4 and 4/5, or 4.8 as a decimal. If you have an equation where the variable you're solving for is inside of an absolute value, you're going to end up with two solutions. One, assuming that the value inside the absolute value is positive, and one assuming that it's negative. So let's take a look at an example here. Here we've got 2x minus 5 inside of absolute value brackets. So what we want to do is we want to solve this to isolate the absolute value on one side, and then solve the equation for x twice, once assuming a positive value, once assuming a negative value inside of here. So let's do that. We'll multiply both sides of the equation by 3 to get rid of this denominator. So multiply by 3 over here cancels the 3's. Multiplying by 3 over here gives us 9x plus 162. and over here we have our 2x minus 5 in the absolute value. So now that we've got this isolated, we need to solve this equation for x twice, assuming once that this is positive and once that it's negative. So to assume that this is positive, all we have to do is take off these brackets and just solve the equation like this. So we'll subtract 9x from both sides and add 5 to both sides. And that gives us negative 7x equals 167. And this is solved as x equals negative 167 over 7. Now, we also have to solve for the case where this absolute value is negative. So to do that, what we're going to do is we'll take what was inside the brackets and make a negative by adding a negative sign in front of the brackets. And so now we'll solve this equation for x. So if you distribute this negative sign through, what we have is negative 2x plus 5. So what we're going to do is subtract 9x from both sides and subtract 5 from both sides. So what that gives us is negative 11x equals 157. So if we solve this now, what we get is x equals negative 157 over 11.
Many times you can use a graph to represent data in a more organized way and in a more visual way. So say we have the equation y equals 2x minus 3. What we can do is plug in a couple of numbers for x and then find out what number we get for y. And then we can come up with some coordinates, plug them in here, and then draw a line representing the values of this equation. So we're going to start out by plugging in 0 for x. So I'm just going to put parentheses like that. So 2 times 0 is 0, minus 3 equals negative 3. So y equals negative 3. So the first coordinate we get is x equals 0 and y equals negative 3. Now we're going to plug in 5 for x. So we're going to put 5 in parentheses. So we get 10 minus 3 equals 7. So y equals 7. So in this case, x equaled 5 and y equals 7. So now we have these two coordinates, and we can just plug these in to this graph right here, and we can get a line. And so we have these dash marks here, so I need to go ahead and label these. So we have this x-axis, which runs horizontal, left to right, and then we have the y-axis, which runs vertical, or up and down. So on the right side of the y-axis, the x-axis is positive. And on the left side, it is negative. This works similarly for the y-axis. Above the x-axis, it's positive, and below, it's negative. So first, we're going to take a look at this coordinate right here. So we have the x-coordinate and the y-coordinate. So we find x first, which is 0, so we're right here. Then we go down to negative 3 and draw a dot. And I'm going to go ahead and put the coordinates right there. Then we look for the x-coordinate first and then the y-coordinate, so we find 5. Then we need to go all the way up to 7, so we're going to need to extend this line a little bit to make it up there. And so we're going to go from 5 all the way up to 7 and draw a dot. And then we just need to draw a line all the way up there. And so if you're using a piece of paper, you can often use a ruler. So I'm just going to attempt to freehand this, which means the line is not going to be very straight, as you can see. But we do need to draw the write the coordinates for that too. And so then we have a line, and so you can go all the way up this line and see different points on it. So you can go, oh, okay, if x equals this certain number, then y is going to equal this certain number, because you can follow it across here. You can go down and find the x-coordinate, and then go across and find the y-coordinate to figure out some other coordinates here, to figure out some other values for x and y. And so here you just have coordinates written on a page. And so It may not mean much to you, it's hard to visualize what that looks like, but here you have a real visual format, a real organized way to view a lot of data and to be able to keep it and comprehend it.
Word problems and addition. Solving word problems is made easier if you know what certain words mean. For instance, here we have a list of words that all indicate addition. So if when you're reading a word problem, you see more than, increased by, some, total, or in all, then chances are you're going to be adding something together. Let's look at an example. 2 more than a number is 15. What is the number? The first thing I'm going to do is translate these words into a mathematical sentence. So 2, I'm going to write the number 2. More than, I know, tells me to add. When it says a number, well, that's something I don't know. What number is it? And so if it's something I don't know, then I can put a variable there, like an X or a Y, or really anything you want to use. Is in math means equals, and then equals 15. So the only kind of trick here is that more than tells you to reverse the order. It's not just addition. It means instead of doing 2 plus X, I'm really doing X plus 2 equals 15. So now you can probably just look at this and see what number you would have to add to get 15. And that number would be 13, which means X is 13. If you don't know by looking at it what the answer is, then you can solve it algebraically here by subtracting 2 from both sides. But again, you would get that your number is 13. Word problems and division. Here we have a list of some words that indicate division. So if you're trying to solve a word problem and you come across the word quotient, per, out of, or ratio, you'll know that you need to divide something. Let's look at an example. If the quotient, there's one of our key words, of a number and 10 is 3/5, what is the number? So again, we saw that keyword quotient, which tells us we're going to be dividing something. We're going to be dividing two numbers. And those numbers we're dividing are a number and 10. And they must be divided in that order. So when we write our division problem, we could write it as x divided by 10, or we could write it as x divided by 10. But it must be in that order. If we reverse it to do 10 divided by x, then that is not what is written here in this problem. That would be if the quotient of 10 and a number. So order is very important. Since it was written if the quotient of a number and 10, then we must have that number first divided by 10. And you'll see here that I put x, and I put an x because we don't know that number. It just said a number. So when we don't know a number, we use a variable in place of that. Let's finish the sentence. If the quotient of a number and 10 is 3/5, is equals 3/5. Now, since I chose to write it this way, x divided by 10 equals 3 divided by 5, it looks like a proportion, and that's because it is one. All a proportion is a ratio equal to a ratio, and that's what I have here. So to solve this proportion, we're going to cross multiply. X times 5 is 5x, and that's equal to 3 times 10, which is 30. And now we need to solve for x. This is 5 times x, and the opposite of multiplying is dividing. So we divide both sides by 5. 5 divided by 5 is 1. 1 times x is x, and that equals 30 divided by 5, which is 6. So the quotient of 6 and 10 is 3/5. And that's true. 6/10 does simplify to be 3/5. Word problems and multiplication. When you come across a word problem that has any of these words, product, times, twice, or of, chances are you're going to have to multiply. Now this is not a comprehensive list of all of the words that would tell you to multiply, but this is a few of them. Let's look at an example. If Marianne opens a bank account with $450 and earns 12% in interest each month, what will her total balance be at the end of the first month? So what they're asking us to find is our total balance. Since I don't know the total balance, then I'm going to have to use a variable for that. So let's say T then is going to be our total balance. And in order to find my total balance, I'm going to have to take what she's starting out with, her $450, and the amount that she earns in interest in that month. So my total balance will be found by taking the starting value and adding the interest. To find my total balance. So to find my total balance, I'm going to have to know the starting value. So we'll use an S for starting value, which is $450. And I also have to know my interest. So we'll use I for interest. And interest is going to be found by doing 12% of the amount of money she has in her account. So we're going to do 12% of $450. Okay, so to find my total balance, I'm going to have to take my starting value and add my interest to that. And my starting value is $450. So my total balance is going to be $450 plus my interest. And my interest, we said, was 12% of $450. And there's one of those words that means multiplication. So in order to find my interest, I'm going to have to do 12% times 450. But first we're going to change our percent to a decimal. So we move our decimal 2 places to the left. So we get 12 hundredths times 450 as our interest. And 12 hundredths times 450 is 54. So our amount of interest that we earned in that month was $54. Therefore, our total amount is $450 plus $54. And then we just add those two amounts together. Therefore, our total amount is $504. And that's how much money we have after 1 month. Word problems and subtraction. When you read a word problem and you see words like difference, less than, decreased by, or fewer, then you know you're going to need to subtract. Let's look at an example. 6 less than a number is 8. What is the number? Since they're asking us what the number is, that means we don't know it. And if we don't know a number, then we use a variable for it. So right here where we see a number, I'm going to put a variable. I'm going to use x. This phrase less than tells us that we need to subtract. So we have 6. We're subtracting. We've got a number. Is an equal sign 8. But less than is a tricky phrase. It does mean to subtract. But again, you have to reverse the order of the things you're subtracting. Like if I said, I have $5 less than Jimmy has. That means that Jimmy has more money than I do. So I'd have to do Jimmy's money minus $5 in order to find out how much money I had. So 6 less than x is going to be x minus 6 is equal to 8. So what number would I subtract 6 from to get 8? That number is 14, so that means x is 14. Now, if you didn't know that the number was 14, then you could solve this algebraically by adding 6 to both sides. So you'd have, again, x equals 14 because 8 plus 6 is 14. Multiples. You can think of multiples as like counting by that number. So for instance, the multiples of 2 would be 2, 4, 6, 8, 10, etc. The multiples of 3 would be 3, 6, 9, 12, 15, 18, etc. The multiples of 4 would be 4, 8, 12, 16, 20, and so on. Sometimes you're asked to find the LCM of 2 or more numbers. The LCM is the least common multiple. Least meaning the smallest, common meaning the same, and multiple. So if we wanted to find the LCM of, let's say, 2 and 3, the least common multiple of 2 and 3, so the smallest number that 2 and 3 have in common, would be 6. So that's the LCM of 2 and 3. The LCM of, say, 3 and 4, the very smallest number that they have in common would be 12. And you can find the least common multiple of bigger numbers, like say the least common multiple of 12 and 15. So 12 would be 12, 24, 36, 48, 60, 72, etc. While 15 would be 15, 30, 45, 60, So if we were finding the LCM of 12 and 15, the smallest number they have in common is 60. So the least common multiple is 60. Multiplying and dividing fractions. To multiply two fractions, simply multiply the numerators and multiply the denominators. 3 times 2 is 6, and 4 times 5 is 20. Then we can simplify. 6 and 20 are both divisible by 2. So divide your numerator by 2 and the denominator by 2. 6 divided by 2 is 3, and 20 divided by 2 is 10. So 3/4 times 2/5 is 3/10. Now there is somewhat of a trick or a shortcut when multiplying fractions, so I'll show you that. 3/4 times 2/5. When you're multiplying fractions, before you multiply, look and see if you can cross cancel. When you're cross canceling, you're looking at a numerator and a denominator. So 3 and 5, if we look at 3 and 5, there's nothing we could divide both of those by. However, you could divide 2 and 4 both by 2. So 4 divided by 2 is 2, and 2 divided by 2 is 1. Then you multiply like normal. 3 times 1 is 3, and 2 times 5 is 10. So cross-canceling saves you the step of simplifying, but you get the same result. Make sure that you don't ever try and cross-cancel numerators with each other. It's only those diagonal numbers that you can cross-cancel. So you cross-cancel a numerator with a denominator. Now let's look at division. We're going to divide 2/3 by 3/4. And you know what's funny about dividing fractions is that you don't. We don't divide fractions. Instead, we copy the first fraction, we change division into multiplication, and we flip our last fraction. So we copy the first 2/3, we change division into multiplication, and we flip the last fraction over. So it's now 4/3. And now we multiply like normal. 2 times 4 is 8, and 3 times 3 is 9. And that can't be simplified, so 8/9 is our answer. When dividing fractions, just remember CCF. Copy the first fraction exactly as it is, change division to multiplication, and flip the last fraction. Proper and improper fractions and mixed numbers. A proper fraction is a fraction where the numerator is smaller than the denominator. For example, 2/3 or 1/5 or 3/7, etc. Improper fractions are where the numerator is larger or greater than the denominator. For example, 5/3 or 8/5 or 9/4. Improper fractions are greater than 1, while proper fractions are less than 1. A mixed number is a number that contains both an integer and a fraction, like 2 and 3/8 is a mixed number. And you can go back and forth between improper fractions and mixed numbers. For example, if we wanted to change 5/3 into a mixed number, 5/3 is equal to 3/3 plus 2/3. 3 plus 2 is 5, so 5/3. Well, 3/3 is just 1 plus 2/3, which is 1 and 2/3. Let's look at one more. How about 9/4? 9/4 is equal to 4/4 plus Well, actually, it's 8/4 plus 1/4. And 8 divided by 4 is 2 plus 1/4. So that's 2 1/4. So as you can see, both of our improper fractions are bigger than 1. But we can also take our mixed number and change that back into an improper fraction. So let's look at 2 3/8. 2 is 16/8. 16 divided by 8 is 2, plus 3/8. We have common denominators, so just add the numerators. 16 plus 3 is 19. So 2 3/8 would be 19/8 as an improper fraction.